At this point, we've learned how to test a multiple linear regression model and how to evaluate the fit of the model based on the significance of the regression coefficients and their confidence intervals, and by the R-square, which is the amount of variability in the response variable that is explained by our explanatory variables. However, we should further evaluate our regression models for evidence of misspecification. Specification is the process of developing a regression model. If a model is correctly specified, then the residuals, or error terms, are not correlated with the explanatory variables. If the data fail to meet the regression assumptions, or if our model is missing important explanatory variables, then we have model specification error. We perform regression diagnostics to try to understand the cause of the misspecification so that we can try to address it. We can assess violation of the assumptions of the linear regression analysis by examining model residuals. That is, we can take a closer look at the E in our regression formula, which is the error or residual estimate. There are many regression diagnostic procedures to choose from. In this course, we will focus on examining residual plots in order to visually evaluate specification error. First, let's add another centered explanatory variable, internet use rate, to our regression equation. Internet use can be considered an indicator of a country's level of modernization. Here is the regression equation for this model and the Python code. This is the same Gapminder model that we tested previously, with the exception that we have added the centered internet use rate explanatory variable. And here are the results. We haven't yet discussed the interpretation of the intercept in detail. The intercept is the value of the response variable when all explanatory variables are held constant at 0. Because we centered our two explanatory variables so that the mean for each variable was equal to 0, the intercept is the female employment rate at the mean of urban rate and internet use rate. So the female employment rate when urban rate and internet use rates are at their means is 44 out of every 100 women. The results also show that the coefficients for the linear and quadratic urban rate variables remain significant after adjusting for internet use rate. Internet use rate is also statistically significant. The positive regression coefficient indicates that countries with a high rate of internet usage tend to have a higher female employment rate. Each observation has an estimated response value, which is also referred to as the predicted or fitted response value based on the regression equation. But we know that this equation does not estimate the observed response value for that observation perfectly. In fact, urban rate and internet use rate together explain only about 18% of the variability in female employment rate. So there's clearly some error in estimating the response value with this model. In this regression model, the residual is the difference between the expected or predicted female employment rate and the actual observed female employment rate for each country. We can take a look at this residual variability, which not only helps us to see how large the residuals are, but also allows us to see whether our regression assumptions are met and whether there are any outlying observations that might be unduly influencing the estimation of the regression coefficient. The easiest way to evaluate residuals is to graph them. First, we can use a QQ plot to evaluate the assumption that the residuals from our regression model are normally distributed. A QQ plot plots the quantiles of the residuals that we would theoretically see if the residuals followed a normal distribution against the quantiles for the residuals estimated from our regression model. The Python code to generate a QQ plot is here. First, we create an object called fig1 that will be our QQ plot. Then an equal sign followed by sm.qqplot, which calls in the qqplot function from the stats model library. In parentheses, we include reg3.resid, where reg3 is the object that contains our multiple regression results, and resid, R-E-S-I-D, contains the model residuals. Then we add a comma and line equals R with the R in quotes, which tells Python to generate a red linear regression line on the plot. What we're looking for is to see if the points follow a straight line, meaning that the model estimated residuals are what we would expect if the residuals were normally distributed. The QQ plot for our regression model shows that the residuals generally follow a straight line, but deviate somewhat at the lower and higher quantiles. This indicates that our residuals do not follow a perfect normal distribution. This could mean that the curvilinear association that we observed in our scatter plot may not be fully estimated by the quadratic urban rate term. There may be other explanatory variables that we might consider including in our model that could improve estimation of the observed curvilinearity.